Well, hello and welcome to the lecture on 3D machine vision. So this lecture is looking at 3D machine vision as opposed to what you normally deal with, which is really 2D. So just starting at the beginning, with 3D vision, we're trying to make sense of the 3D real world. Of course, the real world has got 3 dimensions rather than 2. 2 is a bit of an abstraction. And you're dealing with complicated 3D objects or unusually shaped objects or surfaces. 3D information gives you a big advantage in terms of the richness of the data and the understanding of what you're looking at, really. And as it says here, it's closely linked to artificial intelligence and ability to learn. I mean, humans learn by manipulating things in 3 dimensions. That's how we learn about the universe surrounding us. And it's the same with machines, really. To get an excellent understanding of what you're dealing with, sort of interacting in 3D, combining 3D vision with AI is really a powerful approach. And that's what we've done in the Centre for Machine Vision. We developed specific techniques for recovering 3D data from complicated 3D surfaces or unusually shaped objects. And then we've combined it with deep learning to get very, very useful solutions to complex problems which up to now have been considered not really feasible for solution. So 3D vision navigation, we'll start off thinking of a few sort of classic applications of vision. And one of them, of course, is to have some kind of 3D vision system on top of a mobile robot. And what you might employ in this case would be something like a LiDAR system. So LiDAR is like radar, detection and ranging, but it's using beams of light rather than radio waves. So that would have on top of this device here, something rotating around, and you're getting all this information on the 3D environment around you. It's a good technique, but a little bit heavy and expensive and difficult to implement sometimes, but it's used a lot in civil engineering when you want to get a general idea of buildings surrounding a situation where you want to build something new, perhaps. And self-driving cars would employ this kind of thing and do employ this one. Of course, there's one in the BRL, which was built over at British Aerospace, employing LiDAR amongst other techniques. But it may be that we can get useful information on the 3D environment around us without necessarily having very complicated and expensive sensory systems. We may be able to use deep learning to combine more conventional 2D images and still get a decent idea about our surroundings. But what are we talking about? Well, in 3D machine vision, of course, we're looking at systems that quite often use triangulation. Things like you might have a laser line which is run over a surface, or you might project an irregular pattern onto a surface and then use triangulation to recover it. And we've got a system we spent a lot of money on in the lab, come from a company called 3DMD, which is based in Atlanta, Georgia. We spent about £80,000 on it. And we use it for measuring children's heads to check for asymmetry. It's a condition called plagiocephaly, which affects very young children. And there's a lot of concern amongst parents about the asymmetry. Actually, it largely corrects itself. So it's not that serious a problem a lot of the time, but nevertheless, in more extreme cases, it can be a bit of an issue. So we were measuring the shape of the head and seeing how it changed with the use of different approaches to try and correct it. And what you get a lot of the time in industry is things like reverse engineering. So here you've got a device which probably has a laser shining out of there, it says avoid laser exposure, and it's got a camera and it can triangulate. And so it knows where, if it's scanning over a surface, exactly where each point is in relation to its coordinate frame here in the device itself. Then this is mounted on the end of this precision arm, which is not actually a robot, but each of these revolute joints here has some high precision encoders built in. So it knows the exact position of these rotationary joints here. So it can work out the location of this device relative to the ground coordinate system. And then you can use that to work out the position of all these points on the surface in relation to the sort of ground coordinate system. And here's someone using such a device it's a Faro arm, in fact, is a company. We use this quite a lot. Even nowadays, it's used in inspection of composites, for example, quite a lot. And they're using it at Bristol University for inspecting nuclear reactors, if you can imagine that. And in this case, an engine is being inspected. So we have a high precision device here which is inspecting the exact conditions and location of these engine components. in this case part of a rifle. So you get pretty good accuracy with this approach, but it's a bit cumbersome. As you can see, you need to have this arm all over the place in the position all the time. And of course that limits the size of the work envelope and also the kind of complex operations you might be able to do with the thing really in practice. Other ways of getting 3D data might be from things like CT scanners, computerized tomography, or MRI scans, and this is how you generate all this precision 3D data for these kind of scans. For example, if you decided you wanted a new tooth, maybe you lost one of your teeth and you want a new tooth, then they would do a limited CT scan of your jaw. And actually the reason they do that is that there's a nerve that runs down the side of your teeth here, and if that's damaged when they're putting the new tooth in, then you'd lose a sensation in your face. So obviously they don't want to do that, so they do this CT scan to make sure they know exactly where the nerve is and where they're going to put the tooth. CT scans, by the way, are not something you want to generally be exposed to because there's thousands of x-rays involved. But if you're just having a limited CT scan, just part of the jaw like this, just a one-off, it wouldn't be too bad. But it's not the sort of thing you want to repeatedly be exposed to because x-rays can potentially be harmful. MRI scanners are not harmful because they don't employ x-rays. So when we're looking at 3D vision, we're trying to get this range acquisition up together. And there are two basic approaches to doing that. You have active methods, where you introduce an artificial light source, and then passive methods, where you use natural light. So active methods are things like time of flight, which is where you shine, well, the system shines maybe infrared illumination or something and measures, if you can imagine this, the time it takes for that to come back, and then works out how far away that is, the thing it reflected off. It used to be a very noisy way of doing things, but it's been improved a lot with the latest generation RGB-D cameras. The Kinect was the first one, but they're used all the time nowadays. For example, the technology is coming on very quickly because a few years ago I wanted to get into time of flight. I spent £7,000 on this fancy German time of flight camera, and then now the latest version of the Kinect type of RGB-D camera came out. And that was about £200 or something. So it's coming a lot cheaper and a lot easier to get 3D data. We're doing a lot of research at the moment with these kind of cameras to recover data from human patients to detect certain muscle wasting conditions and also to help them in development of physiotherapy. Projected patterns is where you either project a laser and just triangulate to work out the points on the surface, or that thing I was talking about, the 3D MD system, that was one where you project a pattern of irregular lines, and that is used to help with the triangulation. Photometric stereo I will talk about quite a lot, and that's probably the main technique that we've used in our lab over the last 20 years. We've applied it to all sorts of areas like 3D face recognition, skin analysis, aggregates, a whole range of application areas. Looking at animals. So those are your active methods. Now when it comes to passive methods, using natural light, it's like our eyes would be a passive method, of course, because there's no illumination involved, it's just us detecting the light, natural light. Shape from shading is a bit like photometric stereo, but you've only got usually one light source, or less than a limited number of light sources, and I'll explain this in a bit more detail. Shape from texture, that's where the human eye uses lots of indicators and guides to help work out the shape in 3D of things. It's not just the stereo vision, it's also shape from shading and shape from texture that helps you work this out. Another thing that can help you is depth from defocus. So if you focus on one particular area, then other areas will be defocused, and you can use the amount of defocus to work out the range. Because that's what you're trying to do a lot of the time, you're trying to work out range data. That's where the D comes in. Red, green, and blue, and then D for distance. Human vision. When we use a machine vision system to indicate useful tasks, we're often attempting to replicate or improve upon the observational and deductive capabilities of humans, of course. But how do we perceive 3D form and shape? Binocular stereo, yes. Each eye sees a slightly different image due to parallax, of course. And therefore you get some disparity. In other words, a given point in the real world appears in a slightly different position in the two images in the back of the eyes. And then the difference between that is a disparity. And you use that to work out, the brain does this automatically, how far away something is. But we can still perceive depth with one eye closed, of course. So we get other indicators as well as that. And one, of course, is apparent size. Decreases as distance to observer increases. But the question is the object smaller or further away? Actually, this reminds me of Father Ted I keep talking about. Small, for the little cows, if anybody knows what I'm talking about. But yeah, anyway, of course, that's perspective. And then, of course, we've got parallax effects. The orientation of an object affects its perceived length. But is the pencil becoming tilted or is it getting shorter? It could be a little optical illusion, if you know, or it can be difficult to determine these things sometimes. Human shape perception, shape from shading. This is something the brain uses all the time. The shading can help us indicate the orientation of the surface and therefore the shape of the object. But of course, we've got to be careful to determine whether it really is due to different orientation or whether it's just a change in reflection. And that's where photometric stereo comes in, because that enables us to very well do that. And the two things there we call the bump map. What that is a dense array of vectors, and each vector is a surface normal at that point on the object. So, and then that gives you the three-dimensional orientation information, and then we can very robustly separate that from what we call the albedo, which is a reflection, usually caused by the pigment in the surface, really. So then, to summarize that, we get a combination of multiple visual clues to help us perceive depth, form, and shape. And of course, prior knowledge and experience plays a major part in helping us interpret the real world. And that's where AI tries to emulate those abilities, I guess. But even for humans, sometimes the human vision system can be fooled, of course, optical illusions. Like this floor, which looks like it's got some funny shapes to it, but it's actually flat in a Turkish bath somewhere. Another one I always think of is down the bottom of St Michael's Hill in Bristol. I think it's listed on the wall of a cafe down there. The bricks are in a certain condition. White and black bricks are in a certain combination, and they look as though they're at an angle, even though they're perfectly parallel. Of course, then automating 3D shape perception. Sometimes we need the computer to be able to perceive the 3D shape. It's particularly useful in situations where it's inconvenient, tedious, unreliable, or even dangerous for humans to do this. And here are some examples. Robotic navigation, of course, where we can build up a map in 3D. We could just use some GPS data, maybe, or we could use existing maps to build up this three-dimensional profile, if you like. And then we can use sort of instruments on board aircraft or missiles to measure the actual position and work out how we can follow that profile of the landscape there. Reverse engineering, we talked about before. Reverse engineering, if anybody doesn't know, is where normally in engineering, you go from a drawing, say, a model, to a real-world part. But supposing that you had something like a classic car that was made a long time ago, you probably haven't got the original drawings, but you might have the part that you want to reproduce. So in that case, you would apply a scanner to it, scan the surface. One way of doing it is something like a coordinate measure machine. I don't know if you've seen those. LK is the big operator in that. And the probe that's on the end of the coordinate measure machine arm is usually made by Renishaw. Renishaw up at Wootton-under-Edge developed this probe years ago and made an absolute fortune out of it and sell it even nowadays to the world. And it's very simple, that's why it's so good. The way it works is a very simple, patented idea, which I won't go into here, but you can look it up at the Renishaw probe. And so it just tells you when you come into contact with an object. And then the position encoders on the coordinate measure machine axes tell you exactly where you are in 3D space. And then you can move along tracking a surface and measuring surfaces very accurately. And coordinate measure machines, if you've got the right controlled environment, can measure very accurately down to a micron, say. But the reliability and accuracy of certain types of machine vision scanners are also very high nowadays. I think Renishaw even make one actually. And they've got the advantage, of course, of being non-contact and potentially quicker than tracing a physical probe along the surface. MRI, as I mentioned before, that's the skill that gives you the three-dimensional data directly from, say, bones inside the body. This is quite useful because doctors can then use these three-dimensional models data. They might even build models from it, like rapid prototyped polymer models, and then they can do a sort of practice on operations, on rather complicated bone structure operations, perhaps, where they can all work together and they can collaborate and show each other what they're trying to do and plan the whole operation in detail before they've actually cut any tissue at all. Fruit picking is quite a good one, and this is the kind of thing that could really take off because AI has given us a big breakthrough in the ability to navigate and operate in complicated environments such as your average orchard, and that's why we could stand a good chance of actually doing this nowadays. And in the case of something you can see here, this is pretty straightforward, okay, because you could see with a regular vision system that these apples are red and the leaves are green, so you could identify where the apples are here for picking, okay. But it isn't often this simple because quite often the apples will be of the same color as the leaves, more or less, and that's where our systems would come in, because with our 3D systems we could then measure we get all this cloud, what they call cloud point data, which is data off the surface, and we'd be able to model that and say, okay, this is a shape in 3D, this spherical shape is an apple. You know, this is quite different from what we're seeing off these leaves and branches. So it's three-dimensional. This is a hot area for research, where not a great deal of work's been done, because up till now, the data hasn't been available very well. But the data is getting cheaper and cheaper and easier now. And it's a great area for research for PhDs. And so we've had a lot of PhDs on trying to interpret scenes from three-dimensional data analysis and segment things in 3D. And it turns out to be a lot of the time a lot easier and more reliable than trying to do it in 2D, actually. Industrial inspection. And this is a good one because what you're trying to do here may be fairly simple and pretty boring for anybody to check, but it could be very critical to the correct operation of whatever it is you're manufacturing. We did a project for a company in Cheltenham who were making these synchronizer hubs for pickup trucks that were being sold in the States. And these automatic gearboxes, these are synchronizer hubs. Now, these were machined by means of dropping broaches, if anybody knows what that is, a type of tooling. You drop the broach through the middle of the hub and it carves sort of grooves in the hub according to what you want, according to what you're trying to manufacture. But if you didn't drop these broaches through in the right order, then you get the incorrect hub, which it would look like a normal hub, but it wouldn't be quite right. And you put it into your truck, and then you find out there's a problem, and you've got $2,000 worth of work to replace a $2 part or something like that. So there's a big motivation. So we had a vision system where we were checking the grooves on the side of this synchronizer hub and checking they were as they should be to make sure the manufacturing had occurred according to plan. So what we're trying to do then is we're trying to automate shape perception. The computer can't really, all it sees is a load of data. It doesn't know what's what. So we've got to somehow introduce a level of intelligence into the scene analysis. Things like perspective, as it says, parallax, orientation. How do we get the computer to perceive shape? Yeah, well, traditionally in machine vision, the simple answer to that would be we structure the environment, actually, so that we know that what we're recovering in terms of the 3D data. Nowadays, with the advent of in the latest developments in AI and deep learning and convolutional neural networks, hopefully there's a little less requirement to do the first part, and we can do a little bit more of the second part, where the system can intelligently interpret the 3D information it's capturing and draw conclusions about the scene. For example, if we're developing an automatic vacuum cleaner, we don't want to have to put more effort into ordering the scene for it to go through, the floors, move the chairs into exact positions. We don't want to do that, because if we're not careful, we'd end up putting more work into that than we would just manually vacuuming the floor. So in that case, we want to worry less about structuring the environment, but this is where AI comes in, and that the system can even map the floor automatically and work out when chairs have moved and things have changed around, work out new, it can map it, and the map can be interactive. As the things change, the map's updated. It's got the sensors built into the vacuum cleaner to do that. These are the kind of systems that are coming out on the market now. Dyson's quite big on this. And what Dyson says about it, James Dyson, is that if vacuuming is going to really take off, robotic vacuuming, then it has to be, the robot has to be better at doing it than a human. So I thought it was quite a good observation. So the technology then we have for measuring things in 3D, one of the most commonly used one is laser triangulation. It's triangulation, so we have triangles with an unknown point and known points and vertices. And this is probably the most commonly used technique in three-dimensional machine vision, because all we need is a camera and a laser pattern generator. And the laser pattern generator is usually a line generator. So we have a ray of laser light goes through a cylindrical lens, and that spreads it out into a plane of light, which then impinges on an object. And we can see the difference between where we'd expect it to be if there was nothing there, and where we actually see the line to be. And that enables us to work out the height at each point when the camera's looking down. Then we can work out, we can do that. And if the object's moving along a conveyor, we can scan the shape of the whole thing using laser triangulation. I'll put a slide onto Blackboard, which is worth just a little simple maths behind the triangulation. It's worth remembering the configuration and remembering the equation, or be able to work out the equation that comes out of it. Just a little bit of trig. And this is it, in fact. So we've got a camera normally looking down. This is a schematic kind of showing the laser, and then, well, it says slit, but in reality there would be probably a cylindrical lens, creating this plane of light. And this is where you expect it to hit the ground. This is where it actually hits the top of the object, this distance, and the relationship h equals d tan theta, where this theta angle is fixed. And this box is most likely moving along a conveyor belt. So a little bit complicated in that you need a conveyor belt and so on, but it's something moving. But once you've set it up, it's got the advantage of being reliable and accurate, particularly accurate. And if it's got disadvantages, it would be its complexity and the fact that you've got a laser, which can be a sort of bit of a health and safety risk, depending on the exact setup. It's got another advantage. Of course, the laser can be a bit expensive sometimes, depending on who supplies it. It could be up to £1,000 maybe. So that could be another slight disadvantage. The camera is not too bad normally, of course. We usually spend, I'm just buying a camera at the moment. It's £1,000 for the camera and about £400 for the lens. So that's pretty typical. Industrial camera, hardened steel case and everything. And there's a general case of the maths behind the laser triangulation. This will be in the lecture notes, which I put onto Blackboard, just for anybody who's interested in laser triangulation. Pattern projection, where we have a set of fringes and we project them using a projector, an LED projector, for example, video projector. And we project it onto an object, and then the distortion of these lines helps us work out the shape of the object in 3D. The different difficulties you can have with this approach are that sometimes, depending on the complexity of the thing you're trying to measure, there could be some doubt about where one line ends and where the next one starts. It's not too bad in this case, but if there was more overhang, then it might be difficult to know which line's which. Sometimes people try and overcome that by having color coding of the lines. Another possible disadvantage might be that the projector is only able to focus over a limited range of distances. So if you're trying to measure big distance differences, you may find you can't actually focus on the board. The focusing has to be done manually or something like that. So there we have an example of a schematic with a laser with a pattern generator shining these lines of light over, and then we have the camera. We're triangulating to work out basically the range of each of these points there in order to work out the shape of the surface in 3D. Now, binocular stereo is, of course, another standard way, and I'll put some notes on this on the internet, onto Blackboard as well, with a little bit of maths showing the triangulation and the equations that come out of it. And again, it's worth remembering that analysis and those equations, or being able to derive them is kind of handy. I recommend that. Again, it uses the principle of disparity between two images to calculate the range and thus provide the 3D shape. I mean, in Mars, the European Space Agency use it to recover the Martian landscape in 3D, in Mars, for example. So these are the two main techniques. That's a crater up on Mars they recovered in 3D with this technique. That would be quite a good thing you could recover, because you need a bit of data in the image, generally speaking, to actually be able to do this binocular stereo approach. This is a bit of maths behind it I was talking about. This is the thing I'm putting in addition onto Blackboard as well. But it has advantages and disadvantages. But the technique is also known as photogrammetry. So you can see here we have, some images taken from the surface of Mars, from the NASA Mars rover, and the different apparent position of these rocks, the near ones, is greater than the different apparent position of these ones that are a long way off. So it's using that to work out the range of everything. You can see that very clearly in the color coding here. These are some separation up here. They're much closer together, not surprising. Now, one problem that you might have with binocular stereo when trying to implement it in machine vision is the correspondence problem. So that is the idea of trying to be sure about, for a given point in the real world, where it corresponds to in the two images. And there are ways we can help overcome this, and look for matching patterns in grey level. So if we've got something that's very busy, an image like we've got here, then there's lots of sort of patterns in it which we can use as to help identify points that are corresponding, or matching features, or you could say, okay. So for example, in this simple case, if I was just trying to image the top of a box, and the box was light colour compared to the ground, then I could just very easily see the corners of the box, and I would know that those corners correspond to the two images. I could work out the disparity, and I could work out the range. This is the same thing, just slightly more complicated because the image is a bit more complicated. So another way, and that's why that Mars thing, as we go back up again, that can be done. You can use the approach of pattern matching here, because it's quite a busy image with a lot of features in it, and you can work out, the shape of that corresponds with the shape of that. That's the same point. So it's more difficult if it's the bland image without many features in it. Another way of helping to overcome it, of course, is simply to project a pattern. That system I talked about, 3DMD, projects a pattern in order to help overcome this correspondence problem, to make sure that a given point of the two images is the same point. The problem with that is that the resolution which you can recover the 3D surface in that way with is limited by the detailed resolution of the pattern. Here we are then talking about the corners of the box I was just mentioning a minute ago. You get those vertices. You can obviously match them, the two images. Projected pattern, that's a sort of simple schematic of what we're talking about. In that case, just shine a laser onto a point, and you see the laser dot in the two images, and you know that's obviously the same point, that laser dot, and you can use a disparity to work out the range. Oh, this is actually some images taken from the 3DMD system. So you can see the kind of weird, random kind of, apparently sort of complicated, random-looking pattern that it projects, but it actually isn't that random. It's actually got certain features in it, like here, there's a feature on there, and that's the same point in the two images, because it's got the same shape of pattern now. Yeah, so that is actually, it looks like a photo, but it's not. It's a reconstructed 3D surface, reconstructed quite accurately, down to 150 microns accuracy. And then you could superimpose the bitmap of the face of the child onto it, and making a very realistic 3D interaction. So you can move this around in 3D as though you're in front of the child and examine the shape of the head in 3 dimensions. That's what we were doing. So then stereo vision, you've got the correspondence problem, as I just talked about. Accuracy can also be an issue because it generally isn't very good. We did a lot of experiments over the years with various companies using this, and we found that triangulation generally gives better accuracy than stereo vision most of the time. So, especially when the thing you're trying to measure the distance of is some way away. And the closer the cameras are together, the worse the accuracy will be, generally speaking, the worse the resolution will be, because you'll have fewer pixels to measure the disparity, and therefore less resolution in the measurement of the accuracy. So if you want to increase that accuracy, you can increase that baseline separation, for example, and the focal length of the camera. But the objects must be present, of course, in both views. Photocalorimetry, shape from shading. Now, with this, you know, the question is, can we infer the object shape from the pins? Pin's appearance changes without attitude. And so shape from shading is generally where we only have one light source. The light source over here, in this case, is over here somewhere. We're trying to infer something about the appearance of these objects from that light reflected from this one light source. The human eye and brain does this all the time, of course, to help us infer something about the shape. In this case, lighting from below, the angle and position of the light changes the apparent face, really. We use this in a thing called photometric stereo, which I'm going to come back to a couple of times because it's been so useful for us. Photometric stereo assumes that the reflection from an object is purely diffuse. Okay, so in other words, you have a light in a known position. You have a point where you're trying to work out the brightness of here. You have a surface normal, and you have something called a lighting law, a lighting model. And the lighting model is based, in this case, on Lambert's law. This is the simplest one, really. So you're saying the intensity that you see at this point equals the intensity of the light times a cosine of the angle from the surface normal to the lighting vector. Okay, don't worry if this is a bit unclear to start with. I'll go over this a couple of times. I think it will become clear after a while. So the position of the camera is not part of this model, as you can see. You normally assume you're looking from above. The thing that's part of the model is the position of the light and the orientation of the surface at each point. So it's a way of working out what the orientation is of the surface at each point. This is kind of a schematic for showing that. And we've got a camera, got a light at a certain distance. You're working out these angles at each point across the image. And we're getting this. The advantage of it is that we can work out the angle at very high resolution in terms of we can work it out at every point, every pixel location of the image. So we get a very dense array of surface normals called the bump map. And then we can get a virtual light, move that around, apply lighting model again, and get what we call a visualization in 3D, of a 3D shape of the surface. Get it with all the pigment taken out. I think we'll have some examples of that later on here. You just get the direction of the surface normals. If you want to get the actual shape of the surface, then you have to integrate these gradients to give you back to the original shape of the surface, okay? That's quite worth it. Because the bump map is just a map of vectors. To get back to the actual 3D range data, you've got to do the integration process. We call that going from 2.5D to 3D. Shape from shading, I say that's where you have a single image. Humans are good at it. Can be deceived by makeup, for example. You do this by measuring the brightness of the surface and making simplifying assumptions, such as we've got a single light source, we've got diffuse Lambertian reflections, I say. Surface is smooth, colour, you've got to assume the colour is constant when you're doing the simple shape from shading stuff, which is not always the case. So it's under constrained, we say, but maths is difficult. We've got too many variables to solve it all from a single image. So that's where photometric stereo comes in. You can see in this video here that we've got 3 lights, okay? We've got 3 lights in known positions. We've got the lighting model. We turn one on at a time and capture 3 images. We combine those 3 images to work out the 3 variables, which are the pigment at each point, the reflectivity at each point, okay? And the other 2 are the 2 orientations of the surface normal at each point. And those are 3 unknowns to completely solve it. And that's why we need 3 lights. So we've got 3 equations so we can solve the unknowns. As it says here, the observed brightness at a given point is a function of the reflectivity and the orientation of the surface at that point. Okay. The images, as I say, give us 3 equations for the unknowns. So we can solve it to get the shape and reflectance of the surface at each point and therefore the whole surface. So we need a relationship between the image intensity and the surface attitude, as I was saying. If we're looking at a sphere here, the apparent brightness changes as the angle changes of the surface from the light source, assuming it's lit from above. Yeah. A relationship between surface grey level and surface orientation is what we've got then. And this could be viewed in this way, kind of schematic. Here we've got a light source. These are all the angles that would give you the same apparent brightness due to orientation at this point. So in other words, cone of possible surface normals are about the illumination vector. Okay. But then we can, so that's another way of showing the same thing. We just got here a sphere. There's the illumination. There's the surface normal. These are all the possible orientations of the surface normal vector. Okay. So Under the assumption of Lambert's law, a single light source contains a surface normal cone, if you like. If we imply another light, this is quite a good way of doing it, I'm thinking about it, because it shows how we're constraining the problem. We apply another light, then we also get this brightness, which indicates this cone. So we know that the surface normal vector is somewhere on this cone, it's also somewhere on this cone. So it could be here, but you see it could also be there as well. So we haven't fully constrained it, okay? So that's where we apply the third light source and say, okay, now it's also got to be on this cone somewhere, surface orientation vector. So, the only vector which goes through all three of those cones is there. So we know the surface normal vector is that vector, okay? And the size of the vector would be the brightness. This is the maths behind it, okay? Algebraic formulation. It's a dot product of the vector of the surface normal and the lighting vector that we use to work this out. The intensities of the three lights are here. We get the surface normal vector components, okay? And this allows us to work out the orientation of the surface and the albedo, okay, or the reflectivity of the surface, which we show as here as this Greek letter here, okay? So we can rearrange it if we want to find out surface normal in this way, okay? The maths on this is in Mel's book, actually, surface inspection book, as I recommended earlier. It's in the short loan section of the library. And it's also, you'll find it a lot on the internet, of course. Photometric stereo is the basics of it. Here's a bit of information I found from a book, from some sources, showing, again, what I've just been talking about, the maths behind it. Image intensity vector, photon illumination vector. If anybody's interested in the maths, I put this in just in case you are, okay? Because somebody approached me in one of the years we were teaching this and said, okay, can you give me a little bit more about how you quantify? Because I was just introducing photometric stereo. They said, how do you calculate these things? And I said, okay, I'll go a little bit into the maths behind it. So the surface normal, surface gradient components are worked out here. We call it P and Q. They're the orientations of the surface normal vector. Okay, that's how you work them out from that. And this is what I put all this onto Blackboard, so you can go through it at your own pace and have a look through. And someone was particularly interested and how you find the albedo out. And the albedo is found with the square root of these M coefficients here. So if you read this through, I think you'll get an understanding of the basic sort of vector maths behind this photometric stereo. So it's a case of implementing these calculations on a large scale. It's a bit computationally intensive, and that might be a disadvantage of it. But what we do a lot of the time is that we use MATLAB, which is designed and works in terms of array manipulation. Of course, images are arrays, and this all requires array manipulation. So MATLAB is pretty good for working out photometric stereo. I also did it in LabVIEW once, but LabVIEW is not particularly suited to this kind of number crunching, really. It's more suited to instrumentation and conventional image processing. So photometric stereo, requires on different light sources. You can, of course, use the sunlight from the moving sun over the period of a day and try to implement it in that way. And one time we had an idea, we were approached by the MOD, and the idea was whether we could find improvised explosive devices by looking at different times of day in the desert environment. And yeah, it was quite an interesting idea. We had a look at that. We did some other work for the MOD on photometric stereo, which I'll probably mention a bit later on. So anyway, as it says, if we use numerical integration to reconstruct 3D shape, as I mentioned a minute ago, we get this bump map, which is just the vectors. We integrate them and get back to the shape. We did this project with General Dynamics and EPSRC and Imperial College. And the idea was it's a three-dimensional face recognition system to give you more reliability at airports on face recognition. Because at the moment, I don't know if you're aware, but any existing 2D face recognition system can be fooled by simply holding a photo of somebody else in front of your face. So with this, because it recovers these profiles that you can't really change, like shape of the nose and the forehead, you can't really cover up either. It's a reliable system it gives you much better reliability, up towards 100% reliability in face recognition. That paper I put onto Blackboard for the London Underground work used this kind of approach. And somebody was reviewing that paper before I presented it and said, well, what about if you use 3D printing to actually generate the face profile and then go through using that? And I said, no, that wouldn't really be a way of fooling it, because the system uses a combination of 3D and 2D. So it uses the 3D shape of the face, but also still the 2D characteristics of the shape of the face, in terms of what your face looks like in 2D. So if I had a 3D printed version of my head, the face wouldn't look the same. Okay, and there would be no easy way of getting the face on there realistically, really. And anybody who's mad enough to try would probably just let them through anyway. Anybody who's mad enough to try might, yeah. But it would be extremely difficult to spoof. And that's one major advantage of 3D face recognition. These are from faces of some of the guys in the lab that we recovered. You can see we're getting fairly good recovery of resolution and accuracy as well in these 3D faces. Photometric stereochem, it isolates 2- and 3-dimensional data, as I say. So you can view it as sort of pulling a transfer off a 3-dimensional surface. And this was a tile actually for a swimming pool tile, I think it was. And it was in the slip. This in the slip, this pattern. But it looks at, when we did the analysis, you think of it in terms of pulling off a transfer. The work we did for the MOD was applying, we had applied this camouflage to these objects that we bought, these plastic objects we bought. And you can see we applied it, and largely got rid of the camouflage. This was a project we did for DTS, for the MOD, basically, the STL. Worked quite well, yeah. So the same technique was applied to a dummy, and we had the pattern in the t-shirt the dummy was wearing, and it has some dodgy objects underneath there. We removed the pattern, and then you can also see that we did some curvature analysis on the 3D data we were gathering from this. And by the time we'd done that, we were highlighting these edges. This was meant to be like sticks of dynamite or some sort of explosive device here. Sorry. And it looks like an X-ray by the time you've done that analysis, but that was quite useful, I think, for analysing what's under the clothes. You could argue that, people are going to wear a bit more clothes, or might wear loose clothes, but if you do this continuously, you might get data over a period of time, which would help you, even if you didn't get it immediately, to identify these suspicious objects under here. The DSTL, the MOD were very interested and keen in what we've done, actually. It's turned out quite a nice project. A project that I'm working on all the time, and is one ongoing one we're commercializing, is using the same technique in a thing called the skin analyzer, which we've been developing at UWE over the last 18 years. So the idea of this, it looks at moles and sees if there's any change over a period of time, and also measures the characteristics of the mole. And this helps GPs to determine whether they need to refer the patient to a pigmented lesion clinic, say at Southmead Hospital. The top, there's two parts to it. There's a 2D part at the top. This we can do now. This is where it's a thing called ABCD rules that they use. At the moment it's purely subjective. They all have as a rule. But with this, we can measure these parameters automatically, and we can measure any changes in them and do that reliably. The thing at the bottom is the 3D analysis, where we recover the texture in 3D from the surface of the mole. And we found that an interesting thing, we published about 20-odd journal papers on this, and one thing we found is that the more irregularity there is in the surface of the top of the mole, the more chances there is that it's cancer. So this 3D surface irregularity, randomness, is a bad sign, rather like colour variation in the 2D in that mole analysis is also a poor sign. What I'm really excited by is the idea of employing deep learning to automatically generate new types of metrics in 3D, which would tell you about the presence of different types of cancer. That's something we're trying to get funding for now, but it's a very exciting area for me. Very rewarding to think that you could make something which could save people's lives, really, but save a lot of money for the NHS as well. We used it with about 1,000 patients in Bristol hospitals, but so far it's still a research device rather than a medical device. In other words, you can't use it for diagnostic purposes. It can only be used for, it's still at the research stage at the moment. It's a bit of a complicated problem. There's about 20 odd different types of cancer that can occur, for example. So photometric stereo then, to recap on what we've been talking about a bit, has no correspondence problem, such as you get in binocular stereo. It measures surface orientation rather than depth. It's good for getting textures in 3D. And is active rather than passive because you have these light sources in known positions. So that's the introduction to 3D machine vision. There's rather a lot there, but I'll recover some of the points made there in more detail in subsequent lectures. I'll talk about it a little bit more. I hope that's a good introduction. One of the devices that you can also study a little bit, and maybe I'll put a slide on it, but maybe I'll put something on Blackboard about it, is of course the RGB-D camera, because it's so commonly used and so relatively low cost and really works quite well. RealSense, I'm making one nowadays, for example. It started off with the Xbox, of course, for controlling that, but now we use it for analysing potatoes, we use it in the field, really out in the field, bouncing around on a tractor. I was doing this in Lincolnshire. We use it for monitoring cows, which down here in Glastonbury we've been doing, now it's going around the country. It's Arla using it at about 50 different places around the country, measuring the cow condition, and a whole range of other applications, because we can get this really useful 3D data. So to summarise then, 3D vision, machine vision, is a really hot area, a really powerful area, one that hasn't been used much up to now, but it's really taking off. I think you're going to hear more and more about it. And it's a really interesting, progressive area of machine vision. So I hope that was useful, and I'll see you guys next time.